Hi everyone.
Hello, Pankaj. Hi.
Hello everyone. I'm Sanjay. Uh, will be presenting today. Uh,
Hello.
Hey, good afternoon, everyone.
Hey Jason.
Howdy, Jason.
Sorry, I'm a couple minutes late.
Ages. Yeah.
Let me grab the agenda that I sent out. Hopefully everyone saw that. So I can share it here briefly, and that way we can try to be quick and get to our main presentation that we have for today. Oh, I see, Sanjay, you're already sharing. Okay, fantastic. That's no problem. I don't need to share. You can keep the screen share. Just a couple quick administrative things. Does anyone have any concerns about the minutes from our meeting last time, which was 2 weeks ago? All right, hearing none, then I think we're good. And then quick on the Global Summit, the 29th is the deadline that Jonae Powers had sent to all of the speakers. So if you're a speaker, hopefully you're working on your presentation and you'll have it ready by the 29th. Or if you're in touch with your speakers or any speakers that you know of, then please make sure that they are pointing in that direction because that's less than a week away. It's before our next meeting. All right, so today we've got a special presentation from Sanjay. So Sanjay, thank you so much for joining us and taking your time. I will turn it over to you and you can introduce yourself and your presentation.
all right. So hey everyone. I am a final semester PhD candidate at the University of Michigan, and this work was got published earlier this year. Was a collaboration between a couple of students uh, at my lab. And yeah, we were able to get this published in ISCA, so pretty proud about that. So I will get on with the presentation. All right, so I'll be talking about our system NMP pack, a near memory processing acceleration of a system that enables near memory processing acceleration of scalable de novo genome assembly. All right. So, what exactly is de novo genome assembly? So that's the application at hand. It's about identifying new or unknown genomes from scratch. And this has its applications. For example, identifying DNA from new pathogens or unknown pathogens, or detecting cancer early on by detecting DNA that is being corrupted by the cancer, or targeting therapy by identifying unique genomes in an individual. So all of this requires identifying new or novel genomes. While de novo assembly helps identifying new genomes, genome alignment helps with comparing one genome with an existing genome. And example frameworks include Minimap and BWMM. Imagine sequencing the COVID-19 genome and trying to compare it with existing coronavirus genomes. So that's where genome alignment helps. All right. So yeah. Is anyone able to see the next slide?
I'm still seeing the one that says de novo genome assembly.
Oh, okay. All right. So is the next slide visible now?
It says background.
Okay, cool. All right.
Yep.
That's what we want. So now onto the background. Uh, the state-of-the-art algorithm that implements a de novo genome assembly is based on the debrewing graph, which captures similarities between different sequences of base pairs. So the method starts with the genome chemically broken down and read by sequencers in a lab. This captures subsequences of the DNA within an electronic medium like a file. So basically, the wet lab converts the actual DNA into, say, a string of A, T, G, and Cs. The next step is to break them down further into what we call as k-mers, which are basically k-length subsequences of individual reads. So for practice, we just set k to be 32. Then the debrowing graph, which I guess you've already seen on the slide now, captures the similarities between
Sanjay,
all.
sorry,
Sorry,
you cut out. What do you set for practice K to be?
32.
32. Okay, thanks.
So then the deburring graph captures the similarities between all k-mers and is constructed by looking for a common k minus 1 mer, but with a different suffix and prefix respectively. So in this example, TG is the base pair string that is common across ATG and TGT. And then they are connected because they have a different prefix and different suffix respectively, but still have a common k minus 1 mer TG. These connections can traverse multiple k-mers, eventually helping us reconstruct the original genome. Step 4 prunes and selects chains of these k-mers that cross a minimum length threshold. Length of 5, for example, a length of 5 prunes away the edges between CTG and TGG because connecting these two k-mers is only going to result in a string of 4 base pairs. And finally, these long chains of k-mers are eventually assembled into a long base pair sequence called a config. So, and the hope is that the config captures most of the original genome. All right, I'll just pause here for questions. All right. The deburring graph based genome assembly algorithm, while effective, has very high resource requirements. For example, um, the 10% of the human genome, which occupies 38 gigabytes on disk, needs about half a terabyte on RAM, and eventually expands to 20 times its original memory footprint during during the debrewing graph construction step. And it also doesn't help that the deburring graph construction is NP hard because we'll have to compare each k-mer to every other k-mer in order to identify the edges. And given that this medical technology is based on uh, genomes are advancing, it is quite likely that the amount of genomes that need to be, the length of genomes that need to be assembled might increase in the future, which eventually requires more memory, which eventually requires more compute. So this means that we need a solution that scales with the problem size. The good news is that such a solution already exists. It's called Pacman, and this is the, sorry, okay. This is the state-of-the-art system. Uh, it scales to thousands of nodes on a supercomputer. And because of that, it can occupy, it basically can occupy a lot of RAM because the memory is going to be spread across multiple nodes across the supercomputer, which means that genes that require a terabyte, terabyte scale of footprint can be potentially assembled on such supercomputers. And given that the workload is also split across multiple processes, uh, multiple MPI processes across these nodes. Well, the problem still stands that the memory and compute requirements are still necessary in order to process such a big amount of data. For example, the original system was designed to be run on 1,000 nodes, which is one of the supercomputers that is forgot the name of the lab, but it is located somewhere close to Seattle. That's the name of the lab that the supercomputer is located in. So the problem still stands that this system requires a large amount of compute and memory, which would make it cost prohibitive to implement such systems and implement such systems at a lower budget, and basically, doesn't really help make genome assembly being a more democratic solution. So this necessitates that we find a more resource efficient solution that also scales with the problem size. So the next couple of slides, I'll be talking about, I'll be delving deeper into Pacman. I'll be talking about every step that goes through every step that makes a part of this application. I'll then be going over the high-level profiling that we did of the application, and then zero in on more architectural metrics that help us identify the bottlenecks. After that, I'll summarize the results from the profiling and help us propose a solution based on those insights. All right.
Sanjay,
The first step, yeah.
I would like to make sure that you focus a little bit more on the computational offload part so that we can ask you questions about your API. I don't want us to run out of time and not have time to go into that. So our main interest as a group is on understanding what function you offloaded, and for any de novo assembly operations that you offloaded, what APIs did you offer and what were your positive and negative experiences in that? That's our main interest. I just want to know.
All right. So I have slides about that as well. So maybe, as you said, I will, reduce the amount of time that I spend on, the individual Pacman steps, just to ensure that everyone has the necessary context. Right. All right. So the first step is basically about reading the reads into memory, as good as reading a file. The second step is tallying all the tallying the counts of the various k-mers that we can extract from these DNA reads. The third step is specific to Pacman, where the macro node is a more efficient representation of the deBroglie graph, where the k-mer that is common across multiple, the k-1 mer, which is common across multiple k-mers, is captured as a central element. And then the other k-mers are represented as suffixes and prefixes across this k-1 mer. The fourth step, which is the most important step in this case, is called iterative compaction, where we try to identify k-mers that can be merged in, identify macronodes that can be identified, that can be merged into other macronodes. So this basically helps us lengthen the prefixes and suffixes across the core k-1 mer. And this is also where the potential for the memory footprint increases. All right. And the fifth and final step is pruning and context generation, where we walk through the graph and then generate all the contigs that are of a minimum length. All right. So this was the high level of all the steps in Pacman. Moving on to the profiling. So we identified that iterative compaction was taking the most amount of time. And it also was taking the most amount of memory because of all the multiple reads and writes that was happening as a part of the macro node compaction. And zeroing in on iterative compaction, we found that the CPU was stalling on memory requests most of the time. And we also found that the memory bandwidth utilization was also pretty low. This basically indicates that the CPU, one, was waiting for the memory to get back with its results, and two, the memory was also too slow in getting back with those results.
What tools did you use to get this data?
We used perf.
Okay.
All right.
Quick
So
question on the
yeah,
previous slide. The time there, is that CPU time or wall clock time or some other?
this is wall clock time.
Okay.
So we also zeroed in on the sizes of the macro nodes during iterative compaction, and we identified that with more and more iterations, the number of macro nodes decreased, but then also the sizes of these macro nodes increased. So this is expected because we are trying to compact. We are trying to represent we're trying to represent multiple macro nodes with a few number of macro nodes. And the interesting observation is that most of these macro nodes have a size less than 8 kilobytes. So this helps us inform that the potential for a near memory processing solution. All right. So to summarize all the insights that we gathered from our profiling, so we identified that iterative compaction is the most important step in the sense that it takes the most amount of time and memory. The iterative compaction is memory bound in that it is waiting on requests from memory. And we also identified that most of the data that basically the macro nodes that iterative compaction works on is able to fit within a DRAM row buffer. And hopefully this opens up opportunities to offload this step onto memory. But the problem still remains that the step still occupies a lot of memory because the genome eventually expands to half a terabyte right before iterative compaction. So the solution must break the problem down into a more manageable size. So a quick summary of a quick high-level idea of NMP pack. So it implements channel-level near memory processing. We break down the iterative compaction step into multiple tasks, subtasks, so that we can enable pipelining in these processing elements. We also use a hybrid solution where the CPU works with the near memory processing compute to balance the workload and also split the work between where the CPU takes on work that is too large for the near memory compute. And we also break our problem down into chunks such that the the system is able to fully utilize its memory footprint, memory capacity, while not exceeding its capabilities. All right. So a quick look at the channel level NMP. So maybe this is where your Professor Mehra, your interests are in. So we place the compute at the channel level so that we can reduce so that we can reduce the traffic across channels and keep most of the communication within a channel. And we also use the extra die area to implement network switches and communication so that the processing elements are able to refer to or access are able to access macro nodes in other DRAM chips. So as I said before, we break down we break down iterative compaction into multiple stages. So the API in this case is execute iterative compaction, where we show the processing element two macro nodes, basically one macro node which is which can be a candidate for invalidation, and then the destination macro node, which the smaller macro node will be absorbed into. So the first step is the invalidation check, where we try to figure out which macro node will be the source macro node and which macro node will be the destination macro node. The second step is going P2 is going to
Hey,
calculate the
Sanjay, sorry to interrupt. Can you point with your mouse possibly?
Oh, sorry. Oh, I was on a different
Okay,
screen. Sorry.
sorry.
So this is the first step where we decide which macro node out of the two is going to be is going to be the source for our data. The second step is basically going to calculate the update or the delta necessary to merge the smaller macro node into the larger macro node. The third step is going to apply this update and then write it back to memory. All right. So I just want to pause here because this is the NMP system that everyone's interested in.
Yeah,
Uh,
and
yeah.
I think, this is a good description of the problem. We are also interested in discussing the solution because normally memory channels do not offer communication substrate. So we are very interested in what was the protocol, what sort of messages were flying around, what were some issues that you experienced. Did you create socket buffers or some other abstraction, that kind of thing.
Right. So so we use Ramulator to simulate to simulate the memory. So and how do I put this? So I would say that our system was simulated quite in a detailed manner, but only on Ramulator. So we estimated the necessary time taken for memory traffic across channels and across DRAM chips. So that was not a very fine-grained simulation, but then given that most of the compute happens within a channel, or rather most of the traffic that we detected was mostly located within a channel. The uh, the communication across chips or across channels was necessary to have, but then it was not a very big bottleneck, so to speak. Uh, was that Did that answer your question?
I don't think that we are so worried about everything being bottleneck, but our group tends to focus on technologies like CXL, which you know. So we are very interested in future what could be recommend for how to connect computational memory nodes, such as the one that you have with you know uh, PNM functionality, PNM style design. How would we actually connect that in real fabrics, not just emulation and approximation, right? Which we believe in your methodology, but we now want to know for practical systems that would be built to do this, what can we learn from your work?
Okay. Hmm. So I would say that um, the APIs that we would have used, if we ended up actually fabricating this, would have been limited to simple memory address reads, because what we were able to exploit is that so we were able to exploit the fact that the macro nodes were mostly able to reside inside the DRAM row buffer. So which meant that most of what the compute needed was already right there. So all it had to do was either read in a different part of the channel or just communicate across multiple channels for another macro node, and which would be basically be captured at the entirely within the processing element.
Yeah, and I think that's where the magic is, right? Because normally when you have a CPU, the CPU issues load store instruction into a memory channel, okay, through its load store pipeline. But in your system, actually, if you can go back to that diagram that you had just that moment, yeah, no, the system diagram with NMPPs,
Uh,
yeah, this one.
okay.
So we are looking at this picture and trying to see what if instead of DDR, each of CH0, CH1 through CH7 was actually, some kind of CXL interface. Okay, that these were actually CXL DIMMs, uh, not DDR DIMMs. That's one possible way to look beyond your picture to something that might be real. In which case, you would not need a side channel network bridge because
Yeah.
CXL itself has the potential to be a switching technology. And if that switching technology were to allow two DIMMs to communicate in the way you anticipate, then I think the way to translate what you said in answer to previous question is that the only thing NMPPs need to do to assemble the data is to issue loads to other uh, row buffers.
Yeah, that's what we assume it does. Yeah.
Okay, so then no algorithm works with only data movement, right? So you also need a way of knowing and synchronizing and making some progress in terms of control flow. So what can you answer, like what do you anticipate if there was a CPU sitting where it is shown in your diagram, and if it were to talk to computational memory, what would it say to the computational memories?
Right. So this is where the sort of hybrid CPU NMP system that we proposed comes in. So the first thing that we would query is that, is my macro node able to fit within a row buffer? Or, it's not just a row buffer. We have a more tighter bound where if the macro node needs more than a kilobyte of memory, uh, we have the CPU take over and do the job for us. So that's not the interesting part. The interesting part is if the macro node is below 1 kilobyte, then we just send the compute. It's almost like doing a function call on the NMP. So we
Yeah, but
transfer. Yeah.
it's a very interesting comment, right? Because normal memory channel is only taking load store operations. So what interface and system software do you anticipate so you can do what you're saying?
Right. I think the assumption that we had was that we could write to uh, specific parts of memory, which the memory system, which would interpret as an NMP function call.
Yeah,
So
that's good. This technique is used by other people, thankfully, also. So you're not alone. We call this shadow addresses, right? So if you have some addresses that, writing into them carries specific meaning, then that's good. So we are interested in this protocol, which is, what happens when the function is done? How does the CPU find out at that time?
uh, let me see if hmm, I'm not sure if we simulated that part. I don't think we thought about that. But how would you do it here? I guess we can have the CPU poll certain parts of memory, which would be associated with certain PEs. So if the PE is like done with its processing, then that part of memory could be updated to be marked as 1 instead of 0, or we could have a bunch of states and say
Yeah.
that, yeah.
I think that's a reasonable approach also. I think other people in the call might have different opinion, but um, I'm glad you're thinking in a way that a lot of people in the industry think. We are trying to see how we could enable future software developers to think about NMP and PIM and even standalone processing units in the fabric. How would we enable them to program this without having to do separate code for each type of device? So we are very interested in higher level abstractions that we could wrap around this.
Right. I guess what we could do is take a page out of what um, uh, CUDA already does. So we could have multiple streams of computations associated with each processing element. So you could have one stream per processing element. So everything within a stream is going to be sequentialized, but then operations can happen in parallel across streams. So that could be, and then you could have a function call pointed at a specific stream, and that's basically going to queue a bunch of function calls onto that specific PE. So I guess we could take a page out of what happens already on GPUs these days. So instead of having one GPU, we would have instead of having one device, I guess we would have multiple devices at each and every PE. Yeah.
We are also interested in your addressing approach because you are working with high level code that came from a fairly sophisticated application, whereas memories only work with physical addressing. So when you are in these NMPPEs, we want to know what did you think about translation, and how do you think that might work if you have memories from more than one server?
So we thought of NMP pack to be located only within one server, but then if you want to handle data across multiple servers, um, how do we do that? Well, I think the CPU has to be a part of the data plane because so I guess there has to be some kind of communication between the PE and CPU, saying that I don't have enough data. So please get me the data first, and then uh, resume execution. Or we could. I think the ideal approach is to have a more restricted programming interface where the CPU is able to allocate all the necessary information within memory and then execute and then make the PE function call. So that kind of simplifies our runtime because we assume that the PEs are rather quite uh, dumb. So the CPUs is the actual unit that orchestrates everything. So the assumption that we made over here is that the CPU sets up everything and then the Ps just read data and then are done with it. So because of the rather um, low capacity of the processing elements, I'm not sure if we can have these elements do extremely expressive compute. So once again, referring back to GPUs cannot do everything that CPUs can. So they still have to wait on CPUs to move data. I mean, they still expect uh, CPUs to set up the data before the kernel call is made. So I
So
think, yeah.
let me ask you, when you say you envisioned a single server, is that because for the loads to work across channels and devices, you would need a single physical memory address space?
Yes,
Uh,
yeah. That simplified our design.
I have a question for you, Sanjay. So have you simulated utilization? You described the problem, and correct me if I'm wrong here, but it sounds like at the start all of your macro nodes are small. So all of
Yeah.
the computation would be done ideally in an MP, and your CPU would be twiddling its thumbs at the start, right? And
Yes, yeah.
then as time goes on, your macro nodes get larger. They don't really fit inside of a single channel or a single channel. Um, so then your computation kind of moves over to CPU, and now your NMP isn't really doing anything. So it
Yes.
kind of feels like you would have half utilization. I'd be really concerned about that, that if it's not, if I'm not getting full utilization on both simultaneously, then I'm not really accelerating it, am I?
Right. So the good thing is that while that is a very good observation, uh, it still happens that the NMPs are the things that do most of the work. So even at very high iterations, like for example, this is a specific iteration that is very close to the end. Oh, by the way, this is a y-axis is logarithmic. So the NMP still has around 92% of handles 92% of the macro nodes, whereas the CPU only handles 7 to 8%. So yes, so this is iteration 220 is the last one. So this is the penultimate iteration.
Hmm.
So yeah.
Okay, I guess I was imagining that it kind of kept resolving down until there was like one macro node left.
Oh, so that usually doesn't happen from our experience. So we still have a bunch of macro nodes, but the good thing is that instead of occupying like half a half a terabyte of RAM, once you compact all the macro nodes, it kind of boils down to a few hundreds of megabytes or tens of megabytes.
Okay, so the NMP has a lot of work to do, continues working all
Yes.
the way until the end.
Yes. Yeah.
And then, I mean, what kind of is there any concern for conflicts between CPU and NMP wanting to, request the same data? I guess not, right? If all of the macro nodes are wholly separated, wholly partitioned. It's not that NMP would ever want a part of a larger macro node, right?
Uh, um, no. So before deciding, so the thing is, before deciding whether or not to execute on the CPU or on the NMP, so the decision is made by the CPU, and then
Hmm.
the control is given to NMP if both of them are small.
Right. And I guess last question, do you know how much time you're spending in that scheduling decision?
It's it's an if condition. Just if dot size. So it's not a lot of time. You just check the size of the vector and make the decision.
Hey, Sanjay, I have a quick question.
Yeah.
What would have happened if you did not have the inter-channel and inter-device interconnect? What if CPU was having to move all the data on behalf of all the uh, all the devices?
Then I guess the savings would go down because now the CPU is in the data plane. Um, so without okay, so without the network bridge, um, yeah, how much was that? So if it happens that the uh, both the macro nodes are located within the same channel, uh, it's not a problem. But then what you're saying is, what if the macro nodes are located across different DIMMs? Is that right? Was that
Sorry,
the question?
took a second to come off mute. Yes, that's correct. And I think this is why I was also asking you the question about single server, right? Because in the end, for this solution to really scale, right, um, you will want to uh, just be able to work with, more and more data, right? More and more
Yes,
devices. Um,
yes.
so I think, people like us who are thinking that it would be nice for computational memory devices to be able to talk to each other. And our motivating use cases, we are glad to hear about your application in genomics. My personal motivating use cases have been things like sorts and shuffles, okay, or transposes, where it would help if memory devices could talk to each other to offload a bunch of CPUs, not just one CPU, right? So we have been trying to think about what should we tell CXL people in terms of switching and requirement, and how do we argue about the benefit? Okay, so uh, I need to ask you about the artifacts from your project. Did you open source any artifacts or workload that people can build upon, like multi-node simulation or a bigger workload? And what's your current work like?
Right. So we have not open sourced the artifacts, but I can um, talk to my advisors and see what we can do here. My current work is actually a little. I'm actually moved on to LLMs, so I'm quite a distance from this line of work. Yeah. Uh, but yeah, I mean, I can put in a word to my advisor and ask them if we can open source this. But what I would say is that most of our estimation actually comes from um, getting the tracing the workload and then replaying the trace using Ramulator. So I don't know if hopefully that helps for now. But I can follow up with you on the open sourcing.
That's good. Genomics, while your paper was good, we actually also as a group tend to focus on applications like AI vector databases and also traditional analytics oriented database workloads. So we are very interested in, based on the learnings from your project, um, and seeing more and more computational memory prototypes come out from the memory industry. We are also interested in hearing your thoughts, so would welcome you to join our group meetings, uh, and collaborate in the future as well. But I thank you for answering our questions very patiently.
Of course. Yeah, I'm actually speaking of databases. I have a paper in VLDB. It's going to come in 2026 on accelerating temporal graph mining on GPUs. So I think that might be an interesting application that could be mapped onto NMPs because, I mean, I guess all you have to do is I see the parallels between NMPs and GPUs in that the processing elements are rather quite uh, uh, not so capable, but then the acceleration comes because of the scale of compute. So it's called, the paper is called Mayura. Maybe you guys can. I'll just send a link to the archive paper. Um, in the chat. You guys can, yeah. Yeah, maybe this is an application that we could eventually map to NMPs, and yeah, I'd be happy to work with folks on that.
Okay, sounds good. Jason, I don't have any other questions or comments, but I know I had initially reached out to Nishit, I think your advisor, and he put us in touch with you. So I'm glad we could make this happen. It took a little bit of time, but it's very nice to have you here today, Sanjay.
Thanks, Noel. I was very happy to present our.
So Sanjay, we do have a little bit more time if there's anything else you want to cover.
So most of the I could quickly go over the results. All right.
Sure.
So we have some software optimizations. So so as I already said, we split the work between the CPUs and the NFPs, and the CPUs take up the work that is too big for the NFPs. And we also batch the data by basically doing the work in a piecemeal fashion. Instead of requiring 20 terabytes in one shot, we are able to do the work with just half a terabyte of RAM sequentially. And yeah, I just quickly go over the results. So we are using the human genome as the input to our evaluation. And we are setting a batch size of 10% of genome, as in we iteratively compact only 10% of the genome at a time. Pacman is going to be our state-of-the-art baseline. Our CPU baseline is actually a version of Pacman that we have actually optimized with a lot of extremely simple software optimizations. The GPU baseline is similar to the CPU baseline, but instead of the instead of so this is a simulated baseline, which where we basically traced the CPU baseline and then replayed it with Ramulator running a version of the A100 GPU. CPU pack is going to be a CPU baseline with a bunch of optimizations where we have split the very resource-intensive iterative compaction step into multiple stages, and NMP pack is going to be is the solution, the end-to-end solution, which also executes on the near memory processing end. All right. Yes, a few optimizations that we made. So, instead of using MPI, we ended up using OpenMP. So that reduced a lot of communication latencies. We also because we use OpenMP, we were able to use shared memory. So that once again was able to reduce the amount of data that went between processes. And simple things like pass by reference instead of pass by value actually improved a lot of our reduced a lot of memory data movement. And we were also very smart about using the data structures to ensure that we don't reallocate the memory cycle. So simple optimizations, but it helped us go a long way. So here Pacman is the original SOTA implementation. and the software optimized implementation is the CPU baseline. So simple software optimizations were able to take us around 10x over the over Pac-Man, which is kind of tells you, they could have done a better job. Uh, uh, the the GPU baseline is not very is not comparatively faster than the CPU baseline, and we think this is because it is only an estimation. It is only a rough simulation and not a hardcore GPU optimized solution. A CPU pack, which is going to be a CPU baseline with a bunch of extra optimizations for the iterative compaction step, takes us further and brings us on par with the GPU baseline. But then the GPU baseline is not really optimized for the GPU, so it really is only gives you a very rough idea of what the GPU can achieve. And then finally, the NMP solution, which takes the crown. Uh, uh, the speed up comes from being able to reduce a lot of CPU memory data movement, and this is related to the reducing the number of data stalls. Sorry, the number of CPU stalls on memory requests, and by basically cutting that out, we are able to save a lot on compute.
Sanjay,
Yeah.
couple of questions on this one. So
Yeah.
one is, what's the distribution of loads and stores? Meaning, if you had 100 instructions, roughly how many would be loads and stores? And what's the proportion between load instructions and store instructions in your workload?
Right. So I would say loads are a lot more common than stores. So I'm just looking at my at the paper to get the exact data. All right. So loads are about 2/3 of the total number of memory operations.
Okay.
So yeah.
And
Yeah.
it's very memory heavy.
It is very memory heavy. Yeah.
I see. And you also made a very interesting comment there about benefit of shared address space versus um, like passing by value, you were saying. So, you know, in terms of, common address space and scale up, um, how do you see that like extending past a server? What did you actually need and use? You were using shmem gets and puts in this.
No. Sorry, I didn't get that. Could you repeat that, please?
Were you using OpenMP's gets and puts here or other operations?
Oh no, we were using shared pointers because the threads are in the same memory space, same virtual memory space. It was quite easy for us uh, to communicate between threads. Yeah. So what we found is that it's more important to optimize things algorithmically because MPI simply is not able to achieve the low overhead compute that OpenMP can. So the original authors actually tried to split the compute across individual MPI processes, which was not really a good idea because they lost out on a lot of parallelism that was available within the workload of a single process. So yeah, and but of course you would need something like MPI across servers. So that is something that you cannot avoid.
Actually, some of the benefits of CXL technology are that at up to a certain scale, it can even deliver a coherent uh, coherent virtual address space across servers.
I
Um,
see.
so we as a group have been looking at, how do we actually uh, optimize these systems, So global pointers is something that we had been very interested in ourselves, especially for graph workloads. And anyway, very interesting comments there that this actually mattered in your workload.
Yeah, I mean, it's the problem is where you draw the boundary between sort of processing workspaces, processing namespaces. Here they draw a pretty coarse-grained boundary, so they weren't really able to do much across that boundary. So yeah, that was our observation. Yeah.
And can you explain the comment on the bottom right of your slide? Use queues and heaps efficiently. What did you actually mean by that?
Right. So the original code had kind of misused the STL vector data type, where during iterative compaction the base pairs have to be basically appended to the existing suffix or prefix, and vectors are not really good at doing that. So what happens is so let's say a vector is a linear is stored in a linear fashion. So if you need more memory for your vector, you'll end up reallocating the vector and then reallocating the vector with a bigger size and then copying from the old location to the new location. So yeah, that really takes up a lot of time and memory to do that. So it's repeated reallocations and copies. So we just swapped out these vectors for queues, and then wherever possible, where we needed constant time access, we used fixed vectors instead of dynamically sized vectors.
Thanks for that answer. I know we are approaching the top of the hour. Giving it back to you.
I'm happy to answer more questions. I have time.
Any other questions for Sanjay? Well, Sanjay, we really do appreciate you coming and presenting and educating us on your work. This is definitely quite fascinating and is exactly the types of things we're investigating, as Pankaj had said. So certainly if you want to contribute and participate, we would welcome your involvement.
Of course, thanks a lot, Jason. Yeah, and thanks a lot, Professor Mehra, for inviting me. And yeah, this has been quite the experience. Yeah.
Absolutely.
And I look forward to collaborating. Yeah.
Yeah, look forward to it as well.
Yeah, thank you for the great presentation.
Sanjay, any chance that we could you could send a copy of the presentation that we could upload and make available to everybody on the call?
Yeah, I can. Yeah, I'll work on it.
Yeah, that'd be fantastic.
Right.
We would appreciate that. All right, well, have a great rest of your day, everyone.
Yeah, and Sanjay, come back and talk to us about your machine learning work too. Okay.
Okay.
All right.
Awesome.
All right.
Thank you.
Thanks.
Thank
Bye.
you.